I want to take you through the experiments to determine the focal length of the lenses. To determine focal length, determine the focal of converging what? Lens. So this is what we call a converging lens. Okay, this is a converging lens. Now the converging lenses are of different thicknesses. Now the one which is so thick, the thicker one has a short focal length. The focal length is small. Now those which are very thin, they have high focal length. So we shall have method one. Method one, focusing distant object. So we have this. So we have a screen here. The rays from distant what? Object. This is image I. The distance from here to here, we shall call it focal length. So here we shall say this is a screen. Here we shall say step number one. We shall say that a convex lens is made to focus a distant object. Next, a screen is moved to and fro until the sharp image of the distant object is formed on it. The distance between the lens and the screen is measured and recorded, and this is the focal length of the lens used. So that is number one. Then number two, method two, using a plane mirror. A plane what? A plane mirror. So using a plane mirror, we shall have this. This is a plane mirror. Then mirror. Then we shall put a lens on it, like this. Then we shall have these axes. Then we shall have O, I, the distance. The distance is F. So here we shall now say that a lens is pressed on, the first point is a lens, a converging lens is pressed on the reflecting surface of the plane mirror. A pin is clamped above the lens such that its tip lies along the principal axis. Its tip lies along the principal axis. Next point, you say, the object pin is moved up and what? Up and down until it coincides with its own what? Image. Until it coincides with its own image. The distance from the pin to the lens or the plane mirror is measured and recorded, and this is the focal length of the lens. Then next, using illuminated object. Number three, using an illuminated object. So we have a lens here. Then here we shall have the plane mirror here. Then here we have The screen with the cross wires, the source of what? Source of light. Such that you have this. Like this. So this is parallel and it will be reflected back because this is a plane mirror. Okay. Then here we shall now say, and what is reflected back, we can bring them here to form the final image, which is what? Which is it? So here we shall say that. Okay. In this case, we are using a plane mirror and an illuminated object. We shall say that a lens is mounted in a holder pressed between a screen with cross wires and a plane mirror as shown above. A lens is mounted in a holder and is pressed between the plane mirror and the screen with cross wires. Okay? Then we say the light is switched on. The light is switched on. Then from there we can say that the lens is moved. The lens is moved towards this to and from until a sharp image of cross wires is seen or is formed on the screen beside the wire goes. Okay, the lens is moved to and fro, okay, until the sharp image of the cross wires is formed on the screen beside the crossing wires. The distance from the lens to the screen is measured and recorded, and this is focal length of the lens which has been used. Then we shall have another one using thin lens formula. That's number 4. Using lens formula, thin lens formula. So we shall have, let me say here, this, okay, mounted in the lens holder. This is a table. Then this is the crisp axis. Then here we shall have then here we shall have also another pin such that the tip lies along the principal axis. And then we shall have, let me say, so this is object A. Then this is search pin. We can call it search pin. Search what? Search pin. This is image of. So here this is what? This is distance what? Distance U. This is distance what? Distance V. So we shall now say that an object pin is placed in front of the lens. Number 1 we say an object pin O is placed at a distance U greater than the focal length of the lens, okay, in front of the lens. Next point, a search pin is placed behind the lens and it is moved. A search pin is placed behind the lens and it is moved to and fro until it coincides with the image of O. Until it coincides with the image of O. Then next point is the distance U and V are measured and recorded. Then next, experiment what? Experiment repeated for different values of what? For different values of u. Next point, and corresponding values of v obtained. The next point you tell us that the results are tabulated, including values of u, v, and u plus what? U plus v. Okay? Next point tell us a graph of uv against u plus what? Is plotted. And the slope f is calculated. And this slope f is the focal length of the lens used. So of course you know that 1 over f equals 1 over u plus 1 over v. So here you can see that our f will become product of sum v uv over u plus v. So when you plot a graph of uv against u plus v, change in vertical axis over change in horizontal axis gives you what? Gives the slope. Then another one, there are many methods. Then the other one we can use displacement method. Displacement what? Displacement method. This is it, number 5. Displacement what? Method. So in this displacement method, we are going to make this. We have this one. This is illuminated object. Then we put a table here. Then you have the screen here. This is what? Screen. Then we shall now say this is also battery. Also plate. Then here they have the lens. This is position A. Position A. Then we shall displace it to position 1. This is position B. Okay? Then we shall now set this distance here is what? Is L. Yeah, like that. So in this case we shall now say, okay, we shall now say an illuminated object O is placed behind the crossing wires. Is placed behind the crossing wires. Okay? Or we can say, actually we can say that the cross okay, we can say that an illuminated object O is placed behind the hole. Is placed behind the hole in the screen. Is placed behind what? The hole here. Then we shall say the convex lens is moved. Okay? Is moved towards the screen until a magnified image is formed. So the first thing is, we say, actually can really say, the experiment is set up as shown above. Then we can say, the lens is moved from A towards the screen. The lens is moved towards the screen. Okay. The first we say, the lens is moved towards what? The screen until a magnified image of the cross wires are formed on what? On the screen. The position A on the table is marked. The position A is marked. Then we say the lens keeping the object and the screen fixed, keeping O and I fixed. The lens is again moved to position B. Where? To position B where? A diminished image. A diminished sharp image of cross wires is formed on the screen. Okay? We say that keeping what? Keeping object and the screen fixed. The lens is moved towards what? The screen until a diminished sharp image of cross wires is formed on the screen. The position B of the lens is noted. The distance between AB, D. The distance between AB, D is measured and recorded. The distance between the object, okay, the distance between the illuminated object and the screen L is measured and what? And decoded. Then we say the focal length is what from F equals L squared minus B squared over 4 for F. So, have you known the person now? You say the experiment is set as shown above. Then you say the lens is moved toward the screen until a magnified image is formed on it. The position A is marked. Okay? Then we say it is again moved toward the screen until a diminished image of the cross wires is what? Is seen, is formed on the screen. The position B is marked. The distance between the two marks A and B is measured. The distance between the illuminated object and the screen is also measured and recorded as L. The focal length is good for all this. You remember this one, how to derive it, okay? Then what about inaccessible lens? Inaccessible, using inaccessible tube. Using inaccessible, inaccessible lens fixed in a tube. In a tube. So here we shall have this. Okay. Shall have this. Then here we shall have screen. Then here we shall have the tube is here. So we have this one, like that one. This is A, this end is A, this end is what? Is B. So we shall say the experiment is set as shown what? Above. The experiment is set as shown above. Then we say the tube is moved. The tube is that what? The tube is moved towards the what? The screen until the magnified image is formed on the screen. The end A, the position A. Okay, for example, the end of the screen A is noted. The end of the screen A is what? Is noted. Okay? Then again we say the tube is again moved towards the what? The screen until a clear, diminished, sharp image of cross wires is formed on the screen. Okay? Then we say the end of the tube is measured and the end of the tube is marked. The end of the tube is marked. Let us maybe call it A prime. The end of the tube, A prime, is marked. Okay? So I can say, okay, we said the end of the tube A is marked, then the second one is the end of the tube A prime is marked. So the distance between the two marks, D is measured and recorded. The distance L between the illuminated object and the screen is measured and noted. Focal length is what from L squared minus B squared over 4L. So here what are we saying? We are saying that if I have a tube, suppose this is a tube. Let me say I have a tube. But then this tube, I don't even know where the lens is. So what I will do, I'll fix the lens inside the tube. I don't know where the lens is fixed. So what I'll do, I'll get illuminated object and a screen. So what I'll do, I'll move this tube towards the screen until I see a magnified image. Then I mark at this end. On the table, I mark it on the table. Then again I move towards the what? Towards the what? The screen. Until a diminished what? Image is formed. When the image is formed, which is clear, sharp, and diminished, then the end of the tube here, I mark it on the table. The distance between two marks, okay, is measured and recorded, and that is our D. Then the distance between the screen and the lens, so the screen and what? And the object there is measured and recorded, and that is our A. So the first thing is that the lens is moved towards what? The screen. So the tube is moved towards the screen until a magnified image is formed. The next point is keeping the object and the screen fixed. Okay? Don't forget that word. Keeping the object and the screen what? Fixed. Okay? The tube is again moved towards what? Towards the screen until a diminished sharp image of the cross wires is seen on the screen. The end A of the tube is marked. The distance between the two marks, remember you mark it when you get the magnified image and when you get the diminished image, mark at the very end of the what? The tube on the table. So measure the distance between the two and measure the fixed distance between the screen and the illuminated object, from which you can get this. Is that okay? Then let us go to focal length of concave lens. Determining focal length of concave determining focal length of concave lens. One using a converging lens, a convex lens. And here we shall start with the diagram. We have this. So we shall have an illuminated object. So we have this. Remember, this is the first image formed by what? By the converging lens. Here this one diverges. So you have to move the screen further. You have to move the screen further until you get the final image. So now in this case we shall now say, now which one is our U? This is our U. Then this is our what? Our V, like that. So we shall now start by saying that an object O, the first one, tell us, okay? Tell us that an object O, an illuminated object O, is pressed in front of a converging lens. A converging lens, maybe let's say L1. This is L1, L2. Is pressed in front of a converging lens L1. Then next point we say the screen is adjusted, okay, until a real image is formed on it at I prime. The real image is formed on it. Next point tells us the distance L1, I1. The distance L1, I prime. The distance L1, I prime is measured and recorded. Okay? The next point we say a diverging lens. A diverging what? Lens L1, L2. Whose focal length is to be determined is now placed between L1 and the screen. Is now placed between converging lens and the screen. The next point said the screen is again adjusted. The screen is again what? Adjusted until the final image is formed on it. Until the final image is formed on it. The distance V. The distance V is measured and what? And recorded. The distance V between the converging lens and the screen is measured and recorded. Then next we shall now say that we need to get U. U is equal to, how do you get U? Okay, we need to get. Then another thing is the separation L1, L2. Separation L1, L2 is measured and recorded. The separation L1, L2 is measured and recorded. Then the object distance U is got from the hollow distance, which is L1, I prime, minus the separation, which is L1, L2, but it's inverted. We put a negative. Then we say therefore, 1 over F is equal to 1 over U plus 1 over V. Therefore, focal length is got from 1 over f equals 1 over u plus 1 over v. So here in this case, tell us action of this. What's the action of this? Tell us that an illuminated object O is placed in front of a converging lens. The screen is moved to and fro until a raw image is formed on it I prime. The distance L1 I prime is measured and recorded. The distance from the lens to the screen is measured and recorded. The lens, whose now action of the lens now? Tell us, the lens whose focal length is to be determined is now placed between L1 and I prime. The screen is again moved further until a real image is formed on it. The distance L2 I, which is the image distance V, is measured and recorded. The distance of separation L1, L2 is measured and recorded. The image distance L2 I is measured and recorded, which is V. The object distance U is got from L1 I prime minus L1 L2 brackets negative. Therefore, the focal length is got from 1 over f equals 1 over u plus 1 over v. Is that okay? Then we shall here say that okay, the next method 2, using a concave mirror. Using a concave mirror. That's number 2. So using a concave mirror, how do you draw that one? So we have a concave mirror this side. This is a concave mirror. This is the fifth axis. Okay. Then we shall have the lens. This is the lens. This is the diverging lens. An object is placed here, illuminated object. So we shall have this something in this nature. So that is going to be diverged like this, and then it will come back. So this is to form an image where? To form an image here. So the image I is this set. So this distance here, let me say, this is P, this is the lens L. So we shall now say that an object P, okay, we can say an illuminated object. An illuminated object is placed in front of diverging lens L. An illuminated object is placed in front of diverging lens L. Arranged coaxially with the concave mirror. Arranged coaxially with a concave mirror M of known focal length. Concave mirror M of known focal length. So you can see here that an illuminated object is placed in front of the diverging lens L, placed coaxially or separated with a concave mirror M of known focal length. Then we say the position of the concave mirror is adjusted. The position of the concave mirror is adjusted until the object coincides with its image. Until the object coincides with its image. So we shall adjust here. The concave mirror is adjusted until the object coincides with its image. Okay? Then after that, we shall now say the distance for separation, that is LP, is measured and recorded. Okay? Remember, this one is what? This one is our U. Then this is our what? Our V. The distance of separation is measured and recorded. So this is V, this is U. The distance OL, which is same as U, is measured and recorded. Okay? Then point I is the center of curvature. This is the center of curvature C. Okay? It's the center of what? Curvature. Therefore, to get point, to get V, we shall get the separation is measured and recorded, okay? So to get this V, we shall have the whole distance, which is CP minus LP, but with a negative, okay? Because it's a virtual image. Then we say that from 1 over F equals 1 over U plus 1 over V, the focal length can be obtained. The focal length can be what? Obtained. Is that okay? So this image is normally formed at the center of curvature. The center of curvature. So that means that our V will now become negative of radius of curvature minus LP. Since R is equal to 2 times what? So the points tell us, after the diagram tells us, an illuminated object is placed in front of the lens L, which is placed coaxially with the concave mirror. Then it tells us that the position of concave mirror is adjusted to and fro until the image coincides with what? Until the image coincides with what? With object. Okay? With object. So this one happens when the refracted rays, the reflected back, and they appear to pass through what? Center of curvature. So this means that they are straight in the mirror what? Normally. Therefore, then we shall say that the distance LP of separation, okay, is measured and recorded, and the distance OL, that is object distance, is measured and recorded. Then go ahead and tell us the image distance V is got from the whole distance, which is the radius of curvature, minus the separation, and it will be a negative. Yeah. Now, so that's where we are. We are going to look at examples now. Examples, okay? We're going to look at it. Examples. Example number 1. Example number 1. So example number 1, we shall use this question. Are you seeing it? We shall use that question as example number 1. So in this question we shall say that an object is placed, an object is placed 20 centimeters in front of a diverging lens that is coaxially placed with a concave mirror of focal length 15. So they have given us the focal length. So what does that one mean? It means that, and then they're saying that when the concave mirror is 20 centimeters from the lens, the final image coincides with it. Draw a red diagram to show the formation of final image. So the diagram, I think we can use that one. Let's use this diagram. Let's use this diagram. So this one is of focal length 15 centimeters. The separation is 20. And then from here to here, this becomes our V. But then since this is the center of curvature, our center of curvature will become, the radius of curvature will become R is equal to F, which is 2 times what? 15, which is 30 centimeters. Then they have given us our distance here. This distance is given us. An object is placed 20 centimeters, so this is 20 centimeters. So meaning that our U is equal to 20 centimeters. Then our V, remember it is negative of R minus what? The separation, which is LP, which can be negative. Radius of curvature is 2F, that's a 30, minus the separation, which is 20. Here you get negative 10 centimeters. Then we shall come and say 1 over F equals 1 over U plus 1 over T. So we shall have 1 over F giving us 1 over U. Our U is what? Our U is 20 plus 1 over negative 10. So LCM is 20. So 1 over F will not become, LCM is 20 This is 1 minus 2. Okay? So that means that our F will become negative 20 centimeters. So that is example number 1. That's example number what? Number 1. Then we shall go to example number what? Number 2. This is example number 1. Let's go to example number 2. So example number 2, we shall have this. That is example number what? Number 2. Okay, so this is an object which is placed in front of a diverging lens, and then behind a diverging lens there is a concave mirror. So it says that an object is placed 15 centimeters. Let's use the same diagram. Example number 2. An object is placed 15 centimeters in front of the diverging lens. So this object here is at 15 centimeters. In front of the diverging lens, coaxially placed with a concave mirror of focal length 13. So F here is what? 13 centimeters. Define, then they're saying that when the concave mirror is 20 from the lens, this is 20 centimeters from the lens, the final image coincides with its object. Draw a rod diagram to show the formation of the final image. This is a rod diagram, so we don't have this here. Then this distance from here up to there, it will be 26, because it's the radius of what? Curvature. It's the radius of curvature. So they are asking us find the focal length for the diverging lens. So as usual, we shall now get our V. Our V, it's a negative because the virtual image will be 26 minus what? Minus 20, which is negative 6 centimeters. So 1 over F1 equals 1 over U plus 1 over V. So 1 over F1 will become 1 over U is 15 minus, because it's negative, minus 1 over 6. So our F1 will become, so the substitute properly using our F will become, okay, this is 1 over F1 is equal, this is 30, this is 2 minus, this is 3, this is 5, 2 minus 5. So our F will become 30 over negative 10, which is negative 3 centimeters. Is it negative 3? What is this? Yeah, so it's divided by negative what? Negative 3. So our F becomes negative what? Negative 10 centimeters. So those are the 2 examples that we can I've managed to take you through, but then we have the exercise. So in your time, when you get time, you come and do these numbers. But for consultations, please, you can always get in touch with me through my number, which is 0785 132 106. For consultations or academic purposes, you can always get in my inbox using that. Okay, I'll even put here the email address so that those who can access email address, you can always give me some mails, so that in case you have any problem, challenges, as far as physics is concerned, things can be sorted out. Yeah. So you do those numbers, those 2 numbers. So sometimes like that last number, like this one, where they've given us this kind of diagram, whereby you have this diagram, which is like this, and you have the lens is here. Sorry, this is the lens, and then they are saying that an object is here, an object O is there. So they are saying that the lens does 2 refractions. So there are 2, the ray is refracted twice. So the first one is this. So from here it is refracted like this. You say this, like that. So when it is refracted, of course, it will form the first image here. Now, this first image will act as an object for this one, and this one is going to reflect. It's going to reflect. It's going to because it does not coincide in this question. The image does not coincide with the object. So, since they don't coincide, it means that this one is not reflected back, implying that this one is not normal. Okay, this one is not what? Is not normal. So there is arm of incidence and arm of reflection at here at this point. So it will be reflected back like this. So when it's reflected back, this one forms an image here. Forms an image somewhere here. So now, after forming an image there, that means this one does what? Does refraction. So diverges. So it forms the final image this side. It forms the final image there. So that is how you can just treat these numbers. The numbers of this nature, you can treat them like that. So as now, that is how we can treat those numbers. Okay, therefore, let's first end there.